Hello, this is Professor Merrill Lichty. In this video we're going to talk about one-way analysis of variance, or ANOVA. You'll recall that we learned about two-sample t-testing as a way to determine whether two populations have different means, and analysis of variance is just a simple extension of this from two populations to any number of populations. And it turns out that if we do analysis of variance with two populations, that's really the same thing as doing a two-sample paired t-test. If we have C populations, then the null hypothesis we'll be testing is that mu1 is equal to mu2 is equal to the same value for all of the populations, versus the alternative that not all of the mu's are equal to each other. And the alternative hypothesis can actually happen in lots of different ways. You could have, say, 6 out of 7 population means equal to each other and just one that's not equal. You could have two of the 7 be equal to each other and the rest not equal, or you could have all of them not equal to each other. So there's lots of ways that this can happen. Let's look at a couple of examples to illustrate what it is that we're trying to do with analysis of variance. In the first one, we're interested in the difference in the starting salaries for members of the graduating class depending on a student's major. So in order to collect this data that we need, we're just going to take a random sample of size 20 from the population of these different majors: math, engineering, English, business, and so forth. And this is what we call an observational study, and we'll talk more about what that means in a little while. In the second example, we want to know if there's a difference in success in learning calculus based on the method of instruction. So we've got the traditional lecture courses, online courses, and a blend of the two. And we're going to take 30 students and randomly assign them to one of those courses. So there'll be 10 in each course. And we call this an experimental study or experimental design involving randomization. And the randomization part's actually very important because we want to know if it's the method that is differentiating between the scores, or as opposed to, for example, maybe all the smart kids might decide they can do the course better online. So if they all just signed up for the online version of the course, we wouldn't know if it was the online method or the fact that the smart kids just signed up for the online course. So the randomization is very important. And if you think about this previous example, we didn't have randomization because nobody's going to let their major be determined for them. They're going to pick that themselves, so we can't randomly assign people to the different majors. And that's why we call this an observational study versus an experimental study. So here's another example that's very similar to the last example. And in this case, we have an honors course in mathematics, and there are 3 different methods of instruction: traditional, online, and a mix. And some mathematics researcher is going to look at 15 students, randomly assigning 5 to each group, and then look at their test scores at the end. And here's what the data might look like. This is what we call unstacked data, and this works well with Excel if you're going to use that. You can see we have the groups listed: lecture, online, and blended, and we have 5 observations of each, and then we have the scores. An alternative to that is what we call stacked data, and this is what is preferable to use in Minitab, although Minitab can use unstacked data as well. We'll have 2 columns: the score, that's the score on the test, and then method is a categorical variable that tells us how the student was taught. Before we do any sort of analysis, it's oftentimes helpful to look at pictures of the data, and that's true here with analysis of variance. In fact, you can get a very good idea of what's going on in the data by doing that. So we're going to go graph, box plot, 1y with groups. And we're going to be asked for a graph variable. That's going to be our test score. And we're also going to be asked for a categorical variable, and that's going to be the method of instruction in this case. A categorical variable tells us how the populations are different. And so here's the data plotted. We have a box plot for each of these things: blended and lecture, and then online. And if you look at this, you'll say, well, it looks like online is doesn't perform quite as well as the other ones, and at face value, that's not a bad assessment. But keep in mind that we have very small sample size here, and so there's good potential for a lot of variation. And in fact, we can't really make a statement about whether online is worse than blended or lecture at this point, and that's why we need to do the analysis of variance so that we can get a formal hypothesis test and a test statistic to measure that. Another graph that we can look at is something called an interval plot, and it's just exactly what it sounds like. You go stat Anova interval plot with groups, and again, you're going to have to put in a graph variable and then a categorical variable, and this is what you get back. You see for each of the methods, we get basically a 95% confidence interval, or some level of confidence interval. So for blended, we'd say it's somewhere between like 77 and 88. And what we're really interested in is whether there's overlap between these different intervals. If there is overlap, for example, if we could put a line here at 80, then 80 is in all of those intervals, so I couldn't really dispute the claim that all of these have the same mean. Okay, so let's go ahead and jump into this. We have C equals 3 groups, or factor levels in the study, and we want to test the null hypothesis that mu1 equals mu2 equals mu3 versus the alternative that not all of the mu's are equal to each other, which really means that at least one is not equal to the others. And this is very standard. We're always going to see this type of null and alternative hypothesis when we do analysis of variance. We're going to use an alpha level of 5%, and we'll use what we call the operational approach, which means we're just going to run the analysis of variance and then backtrack and talk about the logic behind the test. In Minitab, if you go stat Anova one way, and we want to use stack data, you'll see something that looks like this. And I've got circled here, response data are in one column for all factor levels. That means we're using stack data. So you'll want to specify that. You also need to put in the response variable, that's the score, and then the categorical variable, or the factor variable, is going to be the method. So here's part of the output that we get from analysis of variance, and you can see that we have quite a bit of information here. First of all, score versus method, that's what we're testing. We have the null hypothesis, the alternative hypothesis, significant level, and then information about the factor. There's 3 levels: blended, lecture, and online. And then we get an analysis of variance table. There's quite a few numbers in here. I'm not going to focus on any of them yet, except for the F value and the P value. The F value is a new test statistic. We don't know anything about the F distribution yet, but we do know about P values, and we get that given to us here for free. So we can determine the conclusion, or the correct decision to make at the alpha equals 5% level, by simply comparing the p-value to the alpha level. And since 0.229 is bigger than 0.05, that means we don't have evidence to conclude that the alternative hypothesis is true, or rather that the null hypothesis is false. And so we're going to go with the null hypothesis, which says that the average performance is not dependent on the method of instruction. Let's talk a little bit more about the F value, or the F statistic, that's given to us in the analysis of variance table. This is very similar to the T value that we get when we do a t-test, either 1 or 2 sample t-test, in that it comes from a probability distribution. And if we want to determine whether we should reject the null hypothesis, we can do that using this F value, as long as we have a critical value to compare it with. Now, to get the critical value, we're going to need to know a little bit more about the F distribution that we're using, and F distributions have what are called numerator and denominator degrees of freedom. And this is because the F value is actually the ratio of 2 numbers. We'll talk more about that later. But Once we have the critical value, which again is based on the degrees of freedom, then we can determine whether we're going to reject the null hypothesis or not. The decision rule always comes from, of course, the alpha level, and with an F-test, it's going to be the upper alpha percent of the test that tells us where to reject. So for example, in this case, we have 2 and 12 degrees of freedom for an F distribution. That means that we're looking at the right tail, and the value 3.885, or roughly 3.89, is going to be our critical value, or the cutoff. So as long as our test statistic is bigger than 3.89, that means we're going to reject the null hypothesis. You can also get this critical value by looking at table E5 in the textbook, and this is going to be a multi-page table with different pages for different values of alpha, and that's because there's 2 different degrees of freedom, and you'll just have to check that out to see how it works. But notice here that the F distribution doesn't look anything like a normal distribution or a T distribution. It's very heavily positively skewed. We can take this value of 1.67 compared to 3.89, and since it's less than 3.89, that tells us that we're not going to reject the null hypothesis. This is the same conclusion we reached by looking at the p-value of 0.229 being bigger than 0.05, the alpha level. And so we have the same conclusion as we had previously, and these are just 2 different ways to go about the same test. Now keep in mind here that we don't have a very large sample size, which means the test is not going to be very powerful. So if we did have a larger sample size, we could very easily get very different results. We've looked at how to do analysis of variance. Now let's look at the theory and the logic and the mathematics behind it. The first question you might have is, why are we calling this analysis of variance if we're testing for differences in the means? Well, that's a good question. And the answer to that question is because we are looking at 2 different ways in which we can have variation. The first one is what we call variation due to the factor effects or the treatment effects, and sometimes this is called the between group variation or the among group variation. In other words, if the source of variation that we see is due to the fact that we have different treatments or different effects, different methods, then we want to be able to capture that and use that to estimate the variation within all of the data. Alternatively, we have what we call variation within the groups. In other words, even if all of the methods were the same, or all of the treatment effects were the same, there's still going to be random variation within each of the groups. And so what we're going to do is make a comparison between these 2 different sources of variation. If the null hypothesis is true, the sources of variation, or the variation, should be roughly the same. If the alternative hypothesis is true, the source of variation A, or the variation that comes from the factors, is going to be bigger than the variation within the groups. It's important to know about the notation that we use. As we've already said, C is going to be the number of groups or the number of treatments that we're interested in. In this example, we have C is equal to 3. Xij is going to be the ith observation from the jth group. So for example, if I said, what's the 3rd observation from the first group, or x31, I would go down here, observation number 3, group number 1, and I get a 91. The first observation from the second group is going to be 80. That's this one here. And J is the sample size for group J. In this example, we have N1 equals N2 equals N3, all equal to 5. And then N is just going to be the total number of observations. So just sum up all of the NJs. Here's the rest of the notation. We've got xj bar. That's going to be the sample mean for group J. So in this example, we have x1 bar, that's just the average down here, 83.2 for group number 1, x2 bar, 77.4, x3 bar, and so forth. X double bar is the average of the averages, or the overall mean. Another way to think of it is the average of all of the data points. And so in this case it's 12 divided by 15, or 80.8. Mu sub j is the population mean for group J, and of course we don't know those because that's what we're trying to estimate. So let's get into the calculations now. The first thing that we want to measure is the treatment variation, or the variation that comes from among the groups. This is called, we're going to get that by calculating what's called the sum of squares among the groups, or SSA. And this is a weighted average. We're going to just sum over all of the groups, j equals 1 up to c, and we take the number of observations times the group mean minus the overall mean squared. So we have 83.2, that's the mean for the first group, minus the overall mean of 80.8, which we calculated on the previous slide. We're going to square that and multiply by 5. We do the same thing for group 2 and group 3, and we get a value for the sum of squares among the groups of 91.6. The second source of variation that we're interested in is the within groups variation, and we're going to calculate the sum of squares within the groups, or SSW, by doing this double sum here. And don't let that frighten you. All it means is we're going to sum over all of the data points. So we're going to take xij, subtract the group mean, and square it. So for the first data point we have 86 right here. The group mean is 83.2, so we take that difference and square it. The second one is going to be 82, this data point, minus 83.2 squared. And we're going to do that all the way down the column until we get to the second column. Here 80 minus 77.4, 77.4 is the mean here, and we're going to square that. And we're going to repeat that for all of the data points until we get our SSW, which in this case is going to be 328.8. Okay, so let's look at this final calculation then, and this is skipping over a bunch of theory and a bunch of math, and I'll refer you to the notes and the text on that. What we have here is the sum of squares among that we just calculated, and we're going to divide that by its degrees of freedom. And anytime you divide a sum of squares by degrees of freedom, you get what's called a mean square. So we're looking to get the mean square among, and we're going to divide that by the mean square within. So mean square within, of course, is just going to be SSW divided by its degrees of freedom, in this case n minus c. And so the numbers that we have are 91.6 divided by 2, that's 45.8, and 328.8 divided by 12, that's 27.4. Take the ratio of those things and you get 1.67. That was our test statistic. Let's look now at the one-way analysis of variance table that's given to us from Minitab, and we'll see that we have agreement with what we just did. The F statistic, of course, is 1.67. The degrees of freedom were 2 and 12. Sum of the squares, 91.6 and 328.8. Mean square were 45.8 and 27.4. Notice the first row is the variation due to the categorical variable, in this case the method, and the second row is the variation due to the randomness, or the random part. So this all agrees with what we did manually, and so that's good. So let's look at this in a little bit more depth here. We just did a test with the F distribution, and we said our rejection region is always going to be in the upper tail. So why is that? If we were doing a two-tailed test in a one sample or two sample procedure, we would have either an upper or a lower tail rejection region. But what happens with analysis of variance is in the numerator we have SSA, and SSA is just the summation of each of the weighted sum for the difference between the group mean and the overall mean. And so if the null hypothesis is true, if all of these means are the same, then this summation is going to be fairly small. If the alternative hypothesis is true and they have different means, then we're going to expect SSA to be large. And that doesn't matter whether one mean is bigger or smaller, as long as the difference between what we observe and for each group versus the overall is big, that's going to give us a big SSA, which is going to give us a right tail rejection region. Let's look at another example. In this case, we're going to be comparing the cost of repairing bumpers. The manufacturer has 4 different bumpers that they're considering putting on their car. We'll call it type 1, 2, 3, and 4. And they're going to perform a test by running the cars into an object at 5 miles per hour and then determine how much it costs to repair each of the bumpers. This is what the data looks like. You'll notice there are 7 observations for each type of bumper, and then we have the cost of repairing the bumper after running it into a wall on a car going 5 miles an hour. So type 1 bumper, the first one costs $315 to fix, and so forth. We have unstacked and we have stacked data, and let's use Minitab to look at the data. So we've got the box plots. We talked about those earlier, and we see for type 1, type 2, 3, and 4, there's quite a bit of variation. In fact, it looks like, based on this, type 1 is more expensive than type 2 and type 3. There's a lot of variation in type 4, so we might not be able to make that claim. If we look at the interval plot, we can plainly see that there is overlap between type 1 and type 4 if you were to draw a line straight across there, but there is no overlap between type 1 and type 2 and type 1 and type 3. So we can get some good intuition about what's going on here, but we really need to run the test in order to formalize this. So let's run this test. We're going to have the null hypothesis that all 4 types of bumpers have the same cost on average, versus the alternative that they're not all equal to each other. Alpha is 5%. In Minitab, using the stacked data layout, we're going to go stat Anova one way, and then for the response variable, we're going to use cost, and for the factor variable, we're going to use type. Here's the output that we get, and based on this output, we can verify that we should reject the null hypothesis, and that goes along with what we initially thought just by eyeballing it. The p-value approach tells us that since 0.007 is less than 0.05, we should reject the null hypothesis and conclude that the repair costs are different for the different bumper types. Alternatively, we could look up degrees of freedom 3 and 24 in the table in E5, or we can use Minitab to get the critical value of 3.01. And since our test statistic of 5.2 is bigger than 3.01, that means we're clearly in the rejection region and we should reject the null hypothesis. Okay, so we've rejected the null hypothesis and we've determined that the average repair cost is not the same for all 4 different types of bumpers. So the natural follow-up question is, which bumpers cost more, which ones cost less? And in order to answer that question, we're going to have to do a little bit more analysis, and we're going to do that in the next section. So let's look at a summary of what we've done so far. Analysis of variance is the process that we use to test whether more than 2 or 2 or more population means vary. There are some assumptions that we have not addressed yet, but they have to do with the randomness of the sample and the assignments to the different treatments, and normality about the population, or at least if we have a big enough sample size, that the central limit theorem will kick in. And then the other big one is that we have equal variance for all the populations, and we'll talk more about those things a little bit later. The hypothesis that we're using is that all of the means have the same are the same value, and the alternative is that at least one is not the same as the others, or in other words, they're not all equal to each other. And we use the F statistic, which is a new distribution we're learning about, and we reject if our test statistic is in the upper tail of the F distribution.